This is AP Calculus AVA, Unit 4, Lesson 5, the Intermediate Value Theorem for Derivatives. The video recording, which is about 11 minutes in the lesson, is a good presentation. But there's a couple of things I thought I'd try to see if I can emphasize and make a little bit clearer. One, what is the intermediate value theorem? The intermediate value theorem, the IMT, intermediate value theorem, says that if we have some interval a to b, right? Some interval a to b, inclusive of the endpoints. Okay? And f of a equals cap a, and f of b equals cap b. Then there exists, or I should say, every output between or on AB exists between cap A and cap B, or on cap A and cap B. Okay, let me see if I can make clear what that means here. So we have some point A and cap A, and B and cap B, input and output. Okay? If a function is continuous, then, and there's no gaps or anything, I can't suddenly just skip over and pick up my pencil. If it's continuous, every output between A, cap A, and cap B must exist, right? Every output. At some point we have to have crossed over every single point in between A and B. And in between, in the range from A, in the domain from A to B, little a to little b. Okay, that's the intermediate value theorem. Now the intermediate value theorem for derivatives, intermediate value theorem for derivatives basically says, intermediate value theorem for derivatives says, on the interval a to b, where f prime of a equals cap a, and f prime of b equals cap b, then every derivative output exists on the interval from A to B, cap A to cap B. Let me give you an example here. Okay, let's say take the absolute value function. Okay, let's say I have some function here, some point here, some value A. Okay, and f prime of A seems to be about -1, right? Let's say it's -1. Let's see if we can clean that up. Okay, over here, f prime of B equals about +1, right? Okay, at the point in between A and B, the point C, we have a bit of a problem. Okay, because the derivative is either -1 to the left or +1 to the right. Here would be the graph of the derivative on the same interval from A to B. So it's -1 here, and then it doesn't exist, and then it's +1 here. Okay, there would have to be necessarily a gap or a jump. This is f prime of x, f prime of x, if this is f of x. Okay, and there would be a gap. Okay, So to change this here so that there is a derivative, we would need to smooth out the curve. Okay, and then every tangent between 1 and -1 would exist in the domain, on the domain A to B. Hopefully that makes a little bit of sense. Basically what it requires is the intermediate value theorem for derivatives requires that there be smooth transition, that every slope exists between two slopes. Not just every output exists between two points, but every slope exists between two slopes. Okay, there's a smooth transition from slope to slope. All right, so that's really kind of the implications of it. Now he also made a special point of the double-sided differential, so I want to take a look at that. Okay, you're familiar with the definition of derivative, where f prime of x is the limit as h approaches 0 of f of x plus h minus f of x over h. That's 1. The alternate definition, f prime of x equals the limit as x approaches c of f of x minus f of c over x minus c. Okay, as x approaches c, the alternate. But the double-sided differential basically says this: f prime of x equals, and I've presented this once before, the limit as h approaches 0 of f of x plus h minus f of x minus h. So we go h to the left and to the right, all over 2h. Okay, so case in point, let's say I've got f prime of, or f of x equals x squared, and I'm interested in finding f prime at 1. I can use the double-sided differential to do this. I can say f of 1.1 minus f of 0.9, 1/10 above, 1/10 below, divided by 2 times 0.1, 2 times 0.1 or 0.2. Okay, for this, that gives me, the double-sided differential gives me 1.1 squared minus 0.9 squared divided by 0.2. 1.1 squared is 1.21. The 0.9 squared is 0.81. 0.2. That comes to 0.4 divided by 0.2, which is 2. And actually, the derivative at 1 of f of x equals x squared is 2. So it really comes out very accurate. It comes out exactly the same. Now this is actually the slope of the double-sided differential is a secant slope. So it's not always deadly accurate, but it's always a good estimate. But if we take the limit on as the differential, as the 0.1 goes down to 0, then we have the true derivative. So double-sided differential, go the same distance above and the same distance below and find the slope of the secant. That's the big idea. The other thing that he focused on the lesson was numerical derivatives on your calculator. And that's great if you have a TI-84 or something like it. Follow his directions. You really need to know how to use your TI-84 or your graphing calculator very well. So if you don't have a TI-84 but you have a different kind of calculator, consult your calculator's information on the internet to find out how to do a numerical derivative. But if you don't have that, you do have Desmos. But Desmos can't be used on the AP test. So use your calculator if you know how, if you're planning to take the AP test. But if you're not, some of you aren't, use Desmos. So let's say I have some function f of x equals x cubed. There are two ways in Desmos to find the derivative. One is using Leibniz's notation, f prime of x. Okay, and notice what it does here. It graphs f prime of x, and the derivative of f prime of x is actually 3x squared. And it makes a parabola, right? I wonder if it'll do f double prime of x. Yes, it will. It'll do the second derivative. It'll also do the third derivative, f prime 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 of x. Okay? And so that actually equals 6 because the derivative of a linear function is a constant. Okay. All right, so that's one way to do derivatives. Another way is using Newton's notation, d over dx of f of x, or you can do d over dx of x cubed, and then you get the same thing. F of x, because I already defined f of x. Okay. Now, if I want a second derivative, I could let's see if it'll do. No. I don't think it'll do that, dx squared. No, it doesn't. It doesn't know what to do with that. So you can take the derivative of a derivative. d over dx. Yeah, and that gives you the second derivative. But Leibniz's notation is certainly simpler. Now, if you want a numerical derivative, all you got to do is insert a number. So if I want the derivative at 0.5, then I would do f prime of 0.5, and it's 0.75. Okay, all right. And I can use that to find the derivative. So f of 0.5 is 1.2.125. So y minus the y value is 0.5 equals the slope f prime of 0.5 times x minus the x value, 0.5. Okay, and there's the slope of the tangent line. Right there. You can see it as I zoom in to 0.5. Yeah. So we have the slope of the tangent right there. Okay. All right. So now you know how to use Desmos, at least, to find the derivative, either numerical or symbolic. All right. Hopefully that helps.